Welcome to part 3 of our titration analysis, calculating stepwise along the titration curve. You'll notice that I managed to cover up this spot twice and reuse this and these pictures here, not just because I'm cheap, but also because I'm lazy. And spoiler alert, I've still got that, and we're going to get some mileage out of it. If you think that looks a little busy, then you can imagine the first draft of this video where this appeared, and then I decided to scrap that and break it into 3 videos. Without further ado, let's take care of business. Part 3, we're going to work with a weak acid. Last time we used HI, and that's got a large Ka value. Today we're going to use HF, which has not a large K value. In fact, it has a K value of 7.2 times 10 to the minus 4th. So I'm going to write our dissociation equation and our K value. This is where I'm going to put the pHs so that later we can compare the pHs here. So I'm going to set this up over here. All right. We have HF this time. Let me make sure I've got that space. We have HF. It's going to be aqueous with our H2O, H3O plus, and F minus. We're going to have a Ka, and this time it is 7.2 times 10 to the minus 4, and that is our H3O plus and our F minus over the HF. If you're wondering why HF is a weak acid while HI is a strong acid, I've got some videos on acid-base structure related to strength. But for right now, let's focus on this situation. Difference once again, Ka for HA is large. Sorry, for HI is large, Ka for HF is not, so we're going to have to do all that ice that I told you we didn't have to do over here. So let me get that filled in. Alright, welcome back. I've got all my ice labeled there. Spoiler alert, we're not going to need ice for those last 4 positions. We will actually need an interesting ice once we get to that one. But for right now, let's match these up and see where we can go. I had to do some paper rearranging here. Of course, when I set that up, I didn't leave room for the pH, so around 700 or whatever this is at this point. Again, I'm just going to carry these values over. I know it's kind of confusing to see that stuff, even though it's the same. So if you're not sure why it's the same, take a look at the last video. But I'm going to go ahead and fill in these values that we had, 0.20 and 0, and then the rest of them, so 0.15 and 0.05. And again, that was just from our stoichiometry, so we could see at the different steps here. Now, something happens here, and we're going to have to change things up a bit, and I'll do that underneath or whatever. But we've got 0 right here and 0.20 right there. And as we know, something else is going to change there. In fact, the something that's going to change is exactly as we had seen for the acid, which is excess hydroxides. But let's take care of what we have for now. All of these numbers came from the stoichiometry. In fact, I guess we could write these in. This one's got 0.05 moles excess base. This is 0.10, 0.15, and 0.20 moles of excess base. Alright, I'm not going to rewrite that. Alright, so here's what we have. This is a true ice problem. We've got 10 to the minus 4th. It's not a strong acid. And I'm going to try and kind of skeleton this out, and then maybe we can hurry through it. But since it's weak, we lose some unknown amount. In fact, we're going to lose some unknown amount each time. And down here, once we get to here, it's going to be minus 0, because we don't have any, right? So again, something special is going to happen there. Up here, we're going to have to go 10 to the minus 7th from autoionization. And we're going to gain our unknown amount. And then we're going to gain our unknown amount. And here's where things change from our strong acid. I'm not going to lose it all. It's going to be 0.20 minus x. This is going to be x and this is going to be x. But now I've got some of this over here, which means it's going to be harder for the equilibrium to go in that direction. All right, so that's how things are going to change. The more stuff I have over here on the product side, the harder it is for that equilibrium to go in that direction. So we got 0.15 minus x, x, and 0.05 plus x now. See? So we had x and x, now we've got that. 0.10 minus x, x, and 0.10 plus x. That should be a plus. All right, 0.05 minus x, x, and 0.15 plus x. So looking at this stoichiometry right here, like this one, when we set up our Ka expression, Ka is going to have to be x squared over 0.20 minus x, right? And then on this one here, you're going to have, just for reference, x times 0.05 plus x over 0.15 minus x. And I'll write these x values down, not that it necessarily matters, but you got x, 0.10 plus x, 0.10 minus x, and then you have x, 0.15 plus x over 0.05 minus x. All right, that is what K is going to be equal to in each of those cases. I calculated those earlier, and we end up with like x equals 1.2 times 10 to the minus second, x equals 2.05 times 10 to the minus third, x equals 7.1 times 10 to the minus fourth, and x equals 2.38 times 10 to the minus fourth, 2.4, ignoring sig figs or whatever. Our pH we're going to calculate the same way we did for our strong acid. It's just the negative log concentration H3O plus. So pH as the negative log concentration H3O plus, which for our purposes here, pH is going to be the negative log of x. All right, and our x is 1.2 times 10 to the minus 2. We end up with a pH of 1.934. So 1.934 is our pH. And then just working our way down again, negative log of x, we end up with 2.689, 3.148, and 3.62 is our pH. All right. Now, looking at this right here, when we dealt with our strong acid, we had 0 of our acid left, and we had 0.20 molar, or 0.20 moles of a neutral salt, right? So we expected our pH to end up 7. Now we have 0 moles of our acid. We have 0.20 moles of a slightly basic salt, right? So HF is a weak acid. Its conjugate is a weak base. And so when we look here, we have a basic solution. And we have to do ice backwards there, essentially. Like, I'm sure there's a bunch of ways to do this, but I'm going to set it up on right here, I guess. So instead of HF, H2O, H3O plus F minus, I don't have HF. I have F minus. And just as I ask my students, like, figure out what you have and what it can do, well, F minus can act as a base. So F minus accepts an H to become HF, H2O donates an H to become OH minus, base, acid, conjugate base. We don't have a Ka anymore, now we have a Kb. I don't need to look that up in a table because I can just get it using our Ka value, since Kw is Ka for an acid times Kb of its conjugate. Kb is just going to be Kw over Ka right here, where that Ka value is the 7.2 times 10 to the minus fourth. All right. This Kb ends up being 1.67 times 10 to the minus sixth. And this is a straightforward ice problem at this point. We have Kb, we have this. 0.20 right there. Not worried about that. 0 of that, 10 to the minus seventh of that. Looks just like all of our other acid-base dissociation ice problems. The only difference is we've got a base and we're figuring out about our acid. We're going to lose x, we're going to gain x and gain x, 0.20 minus x, x, and x. All right. When you solve this, x equals oops, I wrote that backwards in terms of numbers. This number is 1.39 times 10 to the minus 11th. And then x equals the number we had there moments ago, 1.67 times 10 to the minus 6th molar. And that's our x, which is our concentration OH minus, and it's also our concentration HF. Now the catch is pH is the negative log concentration H3O plus, right? But right here we've got an OH minus, so we can cheat that, and we had mentioned it over here on our acid one. You can either do 14 minus POH, which is negative log OH minus, or whatever. In fact, that's what I'm going to do here. Our pH is going to be 14 minus our POH, which is 14 minus or plus the log concentration OH minus. All right, and so when we plug this number in here, we get a pH of 8.22. So our concentration OH minus is this, and we get a pH of 8.22. So I will write that in right there, perhaps in green. 8.22 is our pH. And I think that's a pretty significant number when we're talking about our titration curves. For a strong acid and strong base, you ended up with a neutral salt, and the pH was 7. For a weak acid and a strong base, you ended up with, in this case, F minus, which is a weak base, and our equivalence point ended up at a basic pH higher than 7 at 25 degrees Celsius. So just as our note right here, we can just like see this work here. All right, and although it seems like things are dragging on and on and on here, there's good news, and that good news is if we have excess base, then all of this work carries over, okay? All these numbers are the same as they were here, which is 12.699, right? Because we have those same amounts of excess base, 0.05, 0.10, 0.15, and 0.20. So this is 13.000, 13.176, 13.301. All right, so those numbers end up like that. I want to tie in Henderson-Hasselbalch in a minute, just as a final note on this, but first up, strong acid, lower pH starting, even though the same concentration because it dissociated more. We get this jump as we have our neutral salt and our excess strong acid, excuse me. And then it jumps to a pH of 7, and then that continues going up exponentially with our concentration OH minus. Similarly here, we started at a higher pH. It was less acidic. We had this buffer region, and then all of a sudden we got our jump, and then we had those same excess base numbers. So the only other thing that I want to mention here is the Henderson-Hasselbalch equation, and I want to compare those Henderson-Hasselbalch pHs to these three numbers right here. Not a buffer, not a buffer, not a buffer, just those three are all we can look at. So I'm going to set this aside and jump over to this piece of paper, and we'll see if we can fit the Henderson-Hasselbalch information there. I can probably fit it right there. Let's go with that. So the Henderson-Hasselbalch equation, as we've seen in these other videos, is just relating the pH to the pKa for a buffer system. pH is pKa plus the log of A minus over HA. In order for this to happen, you need both your weak acid or base and its conjugate. All right. So if we look at our possibilities here, I have just the weak acid, no conjugate, and can't find my green highlighter, but we'll note here I have the weak acid, but I don't have the strong or the weak base, so that's not a buffer system. I have both weak acid and weak base conjugate. I have conjugate pair, I have a conjugate pair. I don't have a conjugate pair, I don't have a conjugate pair, I don't have a not conjugate pairs. So as we look at this buffer region over here, that is right here for us. This is our buffer. And that's a place where we can use that Henderson-Hasselbalch equation. Which gives us a pretty quick approximation. We did ice, that's how we got these numbers, but we could have done it this way. And the first step in that, I guess, is to come up with that pKa value. pKa is the negative log of our Ka value. In this case, pKa is the negative log of 7.2 times 10 to the minus 4th, also known as 3.14 for our pKa value. So when we set these up, we're going to use our ratios of these numbers, our HA and our A minus. So this and this, this and this, this and this. For this one right here, we'll have 3.14 plus the log of 0.05 over 0.15. For this one right here, we'll have 3.14 plus the log of 0.10 over 0.10. And for this one, we'll have 3.14 plus the log of 0.15 over 0.05. All right? And looking at those numbers, we find out they're pretty darn close. They're reasonable approximations. So this one ends up 2.666 for the pH. This one ends up 3.142 for the pH. And this one ends up 3.620 for the pH. And again, as we compare that, 2.666, 3.142, and 3.620, within our buffer region, doing this is certainly faster than setting up these ice problems. So that's something to consider. Some people think it's not really worth teaching Henderson-Hasselbalch, but I think it's a fast enough shortcut, especially when you got a bunch of repetitive calculations, that it's totally worth it. We had to do ice here, we had to do a version of ice here, but then we wouldn't have had to do it in any of those situations.